Ever found yourself pondering on how we summarize numerical variables? It's a question that might not keep you awake at night, but it's a fundamental concept in the world of data. Summarizing numerical variables is a way of making sense of data, condensing large amounts of information into digestible summaries. It allows us to identify patterns, make comparisons, and draw conclusions. In this video, we'll be exploring a few key methods for summarizing numerical variables. We start with the 5-number summary, a simple yet powerful tool that can give us a snapshot of our data's distribution. Then, we'll delve into the realm of boxplots, a visual representation that can help detect any outliers in our data. Lastly, we'll examine the sample mean and standard deviation, two pivotal measures that help us compare data distributions in terms of center and spread. Ready to dive into the world of numbers? Stay tuned. First stop on our numerical journey, the 5-number summary. It's simply a set of 5 numbers that give us a quick snapshot of our data's distribution. Let's break it down. The 5-number summary includes the minimum, the Q1 or first quartile, the median or Q2, the Q3 or third quartile, and the maximum. Starting off, the minimum is the smallest number in our data set. It's as simple as that. Now, the first quartile, also known as Q1, represents the 25th percentile of our data. Essentially, 25% of the data falls below which are Q1. Next up is our middleman, the median. This is the middle value of a data set, with 50% of the data falling below it and 50% above it. It's like the balancer, ensuring that everything is evenly spread on both sides. The third quartile, or Q3, is similar to Q1, but it represents the 75th percentile of our data. 75% of the data falls below Q3. Finally, we have the maximum, which is simply the largest number in our data set. So why exactly is this 5-number summary so important? Well, it provides a quick overview of the distribution of a data set. It tells us about the range of our data, from the lowest to the highest value, the spread of the middle half of our data, from Q1 to Q3, and the center of our data set, the median, sometimes known as the Q2, the middle of the data. The 5-number summary provides us with a compact, yet comprehensive snapshot of our data. It's like a passport of our data's journey, telling us where it started, where it's been, and where it's ended up. Remember, the beauty of the 5-number summary lies in its simplicity. 5 numbers, each with a story to tell, working together to give us a concise overview of our data. And that, folks, is the 5-number summary, your first step to summarizing numerical data. Now how about we give our numbers some visual flair with boxplots? Boxplots, also known as whisker plots, or even box and whisker plots, are a fantastic way to visualize a 5-number summary. They provide a bird's-eye view of your numerical data, helping you understand the central tendency, variability, and outliers all at once. So, how do we construct one? Each boxplot is composed of a box with a line or a whisker either side. The box represents the interquartile range, or IQR, which is the range between the first quartile and the third quartile. In other words, the part of the boxplot represented by the box extends between Q1 and Q3. The line inside the box indicates the median, or the second quartile, the Q2, which is the middle value of the data set. The whiskers, on the other hand, represent the spread of the data outside the box. The lower whisker extends from the box at Q1 down to the smallest value, the minimum. Meanwhile, the upper whisker extends from Q3 up to the largest value, the maximum. We also need to consider the upper and lower fences. Speaking of fences, let's talk about how to calculate them now. These are calculated using the interquartile range, or IQR, and help us identify possible outliers in our data set. The lower fence is calculated by subtracting 1.5 times, or 1.5 times, the interquartile range from the Q1, or first quartile. Any data point below this fence is considered a possible outlier. Similarly, the upper fence is found by adding 1.5 times the interquartile range to Q3, the third quartile. Any data point above this fence is also considered a possible outlier. Now, outliers are data points that are significantly different from the rest of the data. They're not necessarily bad or erroneous, but they can skew our understanding of the data if we don't account for them. That's why it's important to identify and investigate them. So, there you have it. Boxplots not only sum up your data neatly, but also reveal its overall shape, variability, and potential outliers. They take our 5-number summary and turn it into a visual feast, making it easier to compare and contrast different data distributions. With boxplots, our numerical data suddenly becomes much more digestible, don't you think? Moving on, ever heard of the term sample mean? Let's unravel it. Imagine you've got a handful of marbles, each of different sizes. Now, if someone asked you, what's the average size of the marbles you're holding? You might be stumped for a second, but then you'd probably add up all the sizes and divide by the number of marbles. That's essentially what the sample mean is. It's the average. In the realm of statistics, the sample mean is a way to summarize numerical data. It's used to give us a sense of the central tendency of a data set. In other words, it shows us a typical value in the data set. If we were talking about the ages of people in a city, the sample mean might give us a rough idea of the typical age of a person living there. But how do we calculate the sample mean? It's simple, really. You add up all the values in your data set and then divide by the number of values. So if we were looking at the heights of a group of people, we'd add up all their heights and then divide by how many people there were. The result would be the sample mean height. There's a catch though. The sample mean is just one piece of the puzzle. It doesn't tell us everything we need to know about our data. For instance, it doesn't tell us how spread out the values are, or if there are any outliers. That's where other statistical tools come into play, which we'll discuss in upcoming scenes. But the sample mean is a great starting point. It's like the heart of your data set, pumping out a steady beat that gives you a feel for the rhythm of your numbers. It's a number that, while it might not tell the whole story, begins to paint a picture of what your data set is all about. So the sample mean isn't as mean as it sounds, right? Even so, the mean is not the median, so don't confuse the two. Last but not least, let's tackle the standard deviation. Now, what is standard deviation? Simply put, it's a measure of how spread out numbers are in a data set. It's like a yardstick that tells us how much the values in our data set varied from the average, or the mean. Imagine a class of students with their heights measured. If most students are of similar height, the heights would cluster around the average, and the standard deviation would be low. But if students' heights vary greatly, then the standard deviation would be high. So, how do we calculate this nifty little number? Well, there are a few steps involved. First, we calculate the mean of the data set. Then, for each number, we subtract the mean and square the result. We then calculate the mean of these squared differences. And finally, we take the square root of that mean. This gives us the standard deviation. Okay, that might sound a bit complex, but don't worry. In practice, it's less daunting than it sounds. And most software or calculators can do this calculation for you. But understanding the process can give you a deeper insight into what standard deviation actually represents. So why do we bother with all this? Well, standard deviation is a crucial piece of the puzzle when we're summarizing numerical data. It gives us a way to compare data sets. For instance, two data sets might have the same mean, but one might have a larger standard deviation. This would tell us that data in the second set is more spread out, more diverse. In essence, standard deviation is a way of understanding the story that our data is telling us. It provides a measure of uncertainty, a sense of the variability within our data. It helps us to not just understand what is typical within our data, but also how much variation there is from that typical value. And that's the standard deviation, your key to understanding the spread of your data. Well, that's a wrap on our numerical journey. We've navigated through the terrain of numerical variables, learning how to summarize and make sense of them. We delved into the 5-number summary, a quintessential tool that gives us the minimum, first quartile, median, third quartile, and maximum of a data set. Then, we explored the world of boxplots. These handy graphs use the lower and upper fences to pinpoint possible outliers, presenting a clear, visual representation of our data's distribution. We also discussed the sample mean, a vital measure of central tendency, helping us locate the middle ground of our data. Finally, we tackled the standard deviation, a measure of spread that tells us how much our data varies from the mean. These tools, when combined, paint a comprehensive picture of our data. Remember, these tools are your friends in making sense of numerical data. Until next time, keep crunching those numbers.